Hello and welcome to our physical sciences lesson. My name is Tem. Today we are looking at electric circuits. What exactly that we want to understand? We want to look at, the different types of circuits. It could be your series, your parallel, and maybe a combination of the two, and some of the very important reminders in terms of, your current, your voltage, as well as your resistance. Right. Okay, so it is within the context of electric circuits. So we'll look at the two types of circuits, which is the series as well as the parallel, and a combination of these two, which is a series parallel circuit. Right, so in a series circuit, all components, right? All components are connected one after the other. This is how exactly you identify a series circuit. So if one component is connected next to each other, then we're saying that it's a series. But also, more importantly about a series circuit is that there is only one path from the positive terminal to the negative terminal of the battery. Now, this brings us to something that is also very important. Remember, in terms of convention or by convention, current moves from the positive to the negative terminal. So if there is only one path for current to actually flow, then we actually having a series circuit. Right, so this is how we identify a series circuit. So this is a simple series circuit whereby we have got a battery or a cell. Okay, so all the current passes through the battery, and the amount of current that passes through this battery, or the total current in this case, is 0.5 amperes. Right, what are we saying? 0.5 amperes passes through the battery. Now, if the first light bulb, let's call this R1 and let's call that R2. So this light bulb offers resistance to the circuit. In other words, the two are actually connected in series, meaning that the amount of current that passes through R1 is equal to the current that passes through R2, which is also equal to the total current in the circuit. Okay, so this is a simple series circuit. Right, so in a series circuit, what are we saying? The current remains constant, or it remains the same at all points. So meaning that the current that passes through the cell, okay, is equals to the total current, which is the current that passes through the first light bulb as well as the second light bulb. Hence, we can conclude that in a series circuit, current remains constant. So if we have had multiple components in a series circuit, all of them, we are saying that they will receive the same amount of current. Hence, we can safely say that in a series circuit, current indeed remains constant. Right. Okay, now let's talk something else about, the current as an example. So if we were to connect ammeters at different points in this single path for which current can actually flow, we are saying that we'll get the same reading. This suggests that there is the same amount of current at any point in the circuit. Hence, we say this is a series circuit. Right. What about voltage or potential difference in as far as a series circuit is concerned? So what are we saying? We're saying that in a series circuit, voltage across the battery, right? We can think of this in terms of total voltage, right? Is divided across each resistor connected in series. Right. Let's say, for argument's sake, we had our two resistors, which is light bulb 1, let's call it R1, and light bulb 2, let's call it R2. Right. So we are saying that the total voltage across the battery, in this case, it's very important for us to point out that the internal resistance of the battery, as well as the conducting wires, as well as the ammeter, are quite negligible. So we will not take the internal resistance of the battery into account. So we are saying that the EMF of the battery actually equals to the terminal potential difference, because we are saying that in this case we shall ignore the internal resistance of the battery. So the total voltage in this circuit is equal to 5 volts, right? Okay, so the maximum voltage is 5 volts. Now we are saying that if there is the same current through the battery, through R1 and through R2, we are saying that the voltage is going to be divided. Now, if you check, you'd realize that the voltage across R1 is equals to 3.75 volts, right? While voltage through R2 is equals to 1.25 volts. Now, we come to a realization that the total voltage is split between R1 and R2, right? What are we saying here? We are saying that V total is equals to VR1 plus VR2, right? This is what we mean when we say the 5 volts is divided between R1 and R2. But one other thing that is also very important to note is that R1, is glowing brighter than R2. What does that tell us? It tells us that, R1 has got a greater resistance than R2, okay? So now, for the same amount of current, right, we said that current through R1 is equals to current through R2, which is current which goes through the battery, okay, which is equals to the total current. Now, the higher resistance of R1 suggests that there will be greater potential difference across R1, and correspondingly, the lower resistance of R2, there will be a correspondingly lower potential difference. However, if you add 3.75 and 1.25, it gives us the 5 volts, right, which is the total voltage. Right. So in other words, we are saying that in a series circuit, the total resistance is the sum of the resistance of each resistor. So if we had n resistors in series, the total resistance is simply a total of all those resistors that are connected in series. Right. Now, let's look at a branch circuit. Now, the term branched suggests that there is more than one alternative path, in the circuit. All right, while in a series we only have one. So a branch is what in many ways would refer to as a parallel circuit, but essentially it is a branch circuit which provides more than one path for the current. Right. So a branch circuit forms when resistors are connected in parallel. So a parallel combination of resistors gives us a branched circuit. Okay. So there is more than one path from the positive terminal to the negative terminal in terms of the conventional current. Right. Here is a typical example of a branch circuit. Right. Now, let's say this is R1, okay, and this is R2, the two light bulbs which are connected in parallel. They provide a greater, a more than one path for current. Now, the total current in this circuit, which goes through the battery, is actually 1.5 amperes, right? So the 1.5 amperes is split between R1 and R2, right? So if we say total current is equals to current that goes through R1 plus the current for R2. This will give us the total current. But also very important to note is that the current through R2 is double the current through R1. Now, what does that suggest to us? It says to us that the resistor with the lowest resistance has the most current, meaning that R2 in this case is actually, lesser than R1. Okay, so less current will go through high resistance. Okay, meaning that R1 is greater than R2, right? So even if you check here, you'd realize that the brightness of R2 is actually greater than that of R1. Why is it so? There is definitely more current passing through R2 because it has got a lower resistance in comparison to R1. Very, very important, right? So in a branch circuit, current is divided, right? Hence, we would say that a branch circuit where there is a parallel combination of resistors is actually a current divider. So in other words, current is split, because we've got more than one alternative path. Right. So hence we can say that the total current in the branches gives us the main current that passes through the cell. So the current through the cell, would want to also think of it in terms of the total current. Right. So here's a simple example. You realize that R1 is actually half R2. Okay. So in this case, if we say this is R1, okay, and then this is R2, all right, we are saying that R1 is equals to twice R2, 2. Okay, so there's more current where there's lesser resistance, but the total current of 1.5 amperes is split between the 10 ohm and the 5 ohm resistor. Very, very important. Okay, so in a branch circuit, current divides, that's a fact, between the resistors connected in parallel. Also, what are we saying? The larger current passes through the smaller resistor. But also, what is important, you know, in a branched circuit is that the voltage remains the same. So total voltage across the battery is equal to 5 volts, right? According to the readings from the simulation. And then again, voltage across, let's call that, just to be consistent, the top one, let's call it R1. So this is R1, okay, that's R2, right? So voltage across R1, okay, is equal to 5 volts, right? And then voltage across R2, again, is equal to 5 volts. So what can we conclude from this branch circuit is that voltage remains constant. So total voltage is equal to voltage across R1, which is also equal to voltage across R2. So voltage remains constant, right? So our voltage remains constant while current is divided, right? So no matter how many resistors we connect or light bulbs we connect in parallel, as long as it's a branch circuit and there are parallel resistors connected, you know, then the voltage across each one of those is going to be constant. So we are saying in not so many words that in a parallel or a branch circuit, voltage remains constant. That's the main thing that we need to take home. Right. So let's talk about resistance in a branch circuit. Right. So in a branch circuit, the equivalent resistance of the branch is calculated using this equation, 1 over R equivalent. Okay, equivalent, sometimes we use the term effective resistance. But remember, we are interested in calculating the equivalent resistance in a branch circuit. So make sure that you actually get the equivalent resistance, not the reciprocal. Very, very important. However, if there are only 2 resistors connected in parallel to each other, we are able to use for only 2 resistors. Okay, this is just a reminder for only 2 resistors in parallel, right? We can use the equation equivalent is equal to product, okay, divided by the sum. This is only applicable for 2 resistors that are connected in parallel, right? Okay. So if we look at the example that we had in the simulation where we had the 10 ohm resistor that was connected in a branch circuit or which is in parallel with the 5 ohms, we can use this formula to calculate the equivalent resistance. You know, R equivalent is equal to the product, okay, which is R1, R2, right, divided by the sum R1 plus R2, okay? So what does that give us? R equivalent, only for 2 resistors, is 10 multiplied by 5, divided by 15. So the 15 is the sum of the 2, right? So our equivalent resistance in this case, there's something that's very important that we need to take note of, right? Then what are we having here? 10 times 5, it gives us a 50, okay, divided by 15. Okay, so our equivalent resistance is 3,33, right? So that's 3,33 ohms. There's something that you need to take note of. The equivalent resistance is actually less than the smallest resistor in this case. So if this is our R1 and our R2 is the smallest resistor, which is 5 ohms. So the equivalent resistance should be below, smaller than the smallest resistance in this case. Right, so that's the stuff in as far as, you know, the branched circuits as well as series. So we'll take a short break for now. When we come back, we'll look at an example of how to approach these types of circuits. See you after the break. Welcome back to our session. Now we are going to focus our attention on looking at the guidelines in terms of, unpacking, a series and parallel circuit where, we've got a combination of both series and parallel. Now that we've looked at each one of them separately to say what exactly happens in terms of current, in terms of voltage and resistance for both the series and parallel circuit. Now let's turn our attention to a combination of the two and look at some of the, the guidelines and the tips in terms of analyzing or understanding these combination circuits much better. Right. So in a combination circuit, there are components that are in series and others that are parallel to each other. All right. So we are saying that there are many possible, scenarios that we can get in as far as, the combination circuit are concerned. So we're only going to look at some of them because of time constraints. So the same approach that we use in the examples will generally apply, in other different scenarios that involve, combination circuit. Now, if you look at this combination circuit, we've got, this resistor, which is actually, let's call this R1, right? Let's call that R1, okay? Let's call this resistor R1, okay, just to use a different color. So all the current passes through R1, okay? So how much current goes through R1 is the total current in this case, which is 0.3 amperes. Now, at this point, you'll realize that at the first branch, in that branch, a certain portion of that 0.3 amperes actually goes to this resistor R2, right? Now, some of the current will go through R3 as well as R4, okay? So in this case, we are saying that the amount of current that passes through R2, okay, is actually part of the 0.3 amperes. But then in terms of voltage, we are saying that the voltage across this resistor is actually equal to the voltage across this one. Why? Because the R3 and R4 are actually in series, right? So if we had the resistance of R3 and R4, we are able to also say, okay, as a single resistor, these two, R3 and R4, actually parallel to R2, right? So this voltage, that if we call it V parallel, this will also be V parallel, okay? So all the voltage is split between, those two. So, and also, once the current gets to that point, now the total current comes through, then we are saying that, in other words, you can realize that R2 is of lower resistance than R3. So in other words, you're saying R3 is actually greater than R2, okay, plus, actually R3 plus, okay, R3 plus R2, okay, let's just get that clear, right? Because we want to appreciate that these two, R3 is actually a single resistor. If we treat it as a single resistor with R4, these two are actually in series, right? So they are parallel to R2, right? So there's a split in terms of voltage as well as current, right? Now, there's many different scenarios. In this case, just note the position of the battery. This is also a combination circuit. Why? Because these two resistors, this one is in series with that one, meaning that the current that passes through each one of them is 0.17, okay? Now, look at the position of the battery. And again, it means that the total current in this case is actually the current that goes through this resistor, which is the same as that one. So what's so special about this type of a circuit is that the position of the battery can be anywhere. So you need to also familiarize yourself with these ones as well. Right. And then another different setup which talks about, the position of the battery. If you look at this one, there is our source, which is two cells that are connected in series. So if these two cells are connected in series, the voltage of of the source then becomes the 9 volts. So in other words, we added those two together, all right? Now, the 0.42 amperes in this case is the total current or the main current that goes through the battery. Okay, the moment we have got that 5 ohms, it means all that current, 0.42, passes through the 5 ohm. And then there is a split in that part of the circuit. Okay, then beyond that, we also have further splits, and then to such a point that all the current will come to that point, meaning that all the current, which is 0.42, will pass through this resistor of 15 ohms. So how you treat this, identify the series parallel, okay? The parts of the circuit which are in series and with the battery. And those that are in series are actually, we are saying that all the current passes through that portion of the circuit. And then the current in all these series components is actually constant or is the same. That's what we are saying. And then furthermore, we can also have a scenario like this. If you look at this resistor, it is in series with the battery, right? So the current through the battery, okay, which is the total current, is the same current in this case, which goes through, let's say, R1. Okay, but in this case, these two resistors are in series. So if we treat these two as a single resistor, it is actually in parallel with this resistor, okay? Because these two, let's say for argument's sake, they're identical. If you add them together, they'll give us greater resistance, which explains why there's less current in that part of the circuit compared to that, right? Okay, so what are some of the important things? You need to also identify the branches in the circuit. The branches will obviously be resistors connected in parallel, okay? So the branches are actually these resistors that are connected in parallel. So the voltage across these branches actually remains the same, okay? This is just a general guideline. So if we're saying that if this is R2 for argument's sake, and R3, and then R4. So we have to first of all get R3 plus R4, right? Okay, if this is a single resistor, it is in parallel with what? R2, right? So in other words, voltage across R2 is equals to voltage across R3 plus R4, okay? Because these two are parallel. So if we treat R3 and R4 as a single resistor, it means that the sum of R3 and R4 is actually parallel to R2. So that's how we kind of break down a circuit in an attempt to simplify it, okay? So when we simplify the circuit using the calculation, we need to be able to calculate resistance of each branch, okay? And also get the equivalent resistance for each parallel combination, and then be able to determine the total resistance in as far as the external circuit is concerned. So in these examples that we use, we ignored the magnitude of the internal resistance of the battery, okay? So these are just a simple example to say the 10 and 10, these two, they give us the 20 ohms, okay? It gives us the 20 ohms. So this 20 ohm is in parallel with that. Okay, that's what we mean as an example of simplifying the circuit. So there is usually more than one way to solve the combination circuit problems, but we need also not forget the use of the Ohm's law, V is equals to I times R. Right. Okay, good people, we'll take a short break for now and then take our discussion forward after the short break. See you shortly. Welcome back to our session. We are still discussing electric circuits, but now we want to change and focus our attention on solving actual circuit problems. In this case, in most cases, we're not going to ignore, the internal resistance of the battery. So we try to apply the guidelines as we have discussed them in the previous segment. Let's look at those. Right, so recall that a combination circuit, there are both series as well as parallel components that are connected through to each other, and there are also different scenarios in terms of the combination circuits. And in these following examples that we'll use, we are not going to ignore internal resistance of the battery. Right, here's a simple question which says, in the circuit diagram, okay, we'll show the circuit, the battery has an EMF of 9 volts and an unknown internal resistance, right? So the ammeter reading is 0.2 amperes. So what do we have here? We are given the EMF.
You cannot go so fast. I am still busy with...
Oh, sorry, Nicole.
You like...
Okay, so we're going to look at examples that involve, a combination circuit, and there are various scenarios that have to do with the combination circuits. Let's bear that in mind, and each, scenario is unique in its own way. But also very important, we are not going to ignore internal resistance of the battery in the examples that will follow, right? So here is a simple question just to get us started. It says here, in the circuit diagram that I will show, the battery has an EMF of 9 volts and an unknown internal resistance, and the ammeter reading is equals to 0.2 amperes. Right. Okay, so this is the circuit. What do we have? We are given the EMF, which is equals to 9 volts. We are also told that the internal resistance is unknown, okay? So that's not a trench mesh. And then we are given the 3 resistors there in the external circuit, right? So what is the first question? The first question says, calculate the current through the 5.5 ohm resistor, right? So if you look at, we want the current that goes through 5.5 ohm resistors. Okay, so what do we have here? We know that these 2 resistors are actually connected parallel to each other. Okay, so if we have the current that goes through the 11 ohm, we can also get the current that goes through the 5.5 ohm. But remember, the 11 is double 5.5. So whatever current goes through 11 ohms is actually equals to half the current that goes through the 5.5 ohm. Okay, so we can do this in many ways. We can first determine the voltage across the 11 ohms. So V across the 11 ohms is actually equals to, current multiplied by that resistance. So the current, we are told, through the 11 ohm is 0.2. Okay, the resistance is 11. Okay, so what is the voltage across the 11 ohm? It's equals to, if we go to our calculator quickly, it says here 0.2 multiplied by 11. Okay, this gives us 2.2, right? So that's 2.2. Okay, that's 2.2 volts. So voltage across the 11 ohms is equals to voltage across the 5.5 ohm resistor. Why is it so? Because these 2 are connected in parallel. So V across the 5.5 ohms, okay, is equals to current multiplied by resistance. So that V is 2.2, right, is equals to, we're looking for the current, that is 5.5 ohms, the resistance. So the current that goes through 5.5 ohms is equals to, right, if we go to our calculator, what do we have there? We have 2.2, okay, divided by 5.5, okay, it's 5.5. Okay, what do we get there? We get 0.4, right? So the current is 0.4 amperes. You'll realize that the current that goes through 5.5 is actually double the current that goes through 11 ohms. Very, very important. Okay, now we want to calculate the internal resistance of the battery. That's the next question. Right, here's the circuit alongside. Now we know that E is equals to I, okay, R plus R, okay? But we're interested in the internal resistance of the battery. But now, bear in mind that if this is 0.2 amperes, okay, this is going to be what? 0.4 amperes. So this is a parallel combination or a branch. So the total current in this circuit is actually equals to 0.6 amperes, right? So we want to determine the magnitude of internal resistance. So we need to treat this as a single resistor because this is a parallel combination. So our R parallel, we can use product over sum. Why? Because these two are actually connected in parallel. So the product is 11 multiplied by 5.5, right? Divided by the sum, 11 plus 5.5. So our R parallel is actually equals to, if we go to our calculator, what do we have? We have got 11, okay, multiplied by 5.5, okay, divided by the sum of that, which is 16.5, okay. So the R parallel is, in other words, is equals to, you can even leave it in that form as 11 over 3, right? Over 3 ohms. But then our total resistance in this circuit, right? Our total resistance in this circuit, which is R parallel, is equals to 11 plus the 11 over 3, okay? So our R total for the external resistance then becomes, if we calculate that, we get 11 over 3 plus 11, because that is in series, okay? What do we get? We get, 44 over 3, okay? 44 over 3 ohms, right? So we are here now, right? We've got the total, which is the 9 volts there, the EMF is equals to the total current. We've got the total current there, which is equals to 0.6, right? And then the total resistance is 44 over 3, okay, plus our internal resistance R, right? So we are looking for our internal resistance. So what do we have? If we isolate R, we'll get 9 divided by 0.6, okay, minus, okay, if we transpose that 44 over 3, it will give us our internal resistance. So our internal resistance in this circuit, okay, if we go to our calculator, what do we have? We've got 9 divided by 0.6, okay, minus, okay, another fraction, which is 44, okay, over 3. The reason why we're doing this, so that we can only round off at the end. So our value for our internal resistance is 0.33 ohms, right? So it's 0.33 ohms. This must be written next to 2 decimal places, right? So this is just an example of how we can determine the internal resistance. Right. Now, in the very same circuit, we are being asked that whether, the battery still has the same EMF. Then the question says, will the ammeter reading increase, decrease, or remain the same if the 5.5 ohm resistor is removed? Right. So let's appreciate something here. This has to do with our understanding of the circuit. What are we saying? We are saying that the 5.5 ohm resistor, which was connected in parallel with the 11 ohms, now it's no longer part of the circuit. How does that affect the ammeter reading? Now the reading of the ammeter is based on the current passing through the 11 ohm resistor, right? So if we remove this 5.5 ohm resistor, effectively what does that do to the effective resistance? So number one, what's going to happen? Total resistance will increase, okay? So if total resistance increases, why? Or maybe just to explain why, how we arrive at that. The reason why the effective resistance increases is because now we have no resistors in parallel. While adding resistors in parallel decreases the effective resistance. So the total resistance here we're talking about is the effective resistance, right? Take note of that. So if the effective resistance increases, what happens to the current? Okay, the current is definitely going to decrease, okay? So total current decreases. So that's the argument. Okay. So if the total current decreases, it means then without the 5.5 ohm resistor, what's actually going to happen, the ammeter reading will get lesser. Why? Because now instead of the earlier value of total resistance, we'll have a total resistance, an equivalent resistance of equals to 22 ohms. So this is an increase in resistance. Now the total current will definitely decrease. Hence the ammeter reading decreases. So the ammeter reading is going to decrease. That's how we actually arrive at that. It's very, very important for us to try and follow the argument in terms of how we manage to get to that. So what is important is also that how we reason out our answer. So yes, it is a multiple choice, increase, decrease, remain the same. However, how we arrive at that must be, backed up or, by some sort of thinking, because now we're saying that fewer resistors in parallel or no resistors, as was the case in parallel, then the effective resistance of the circuit will actually increase. How does that affect the total current in the circuit? Is going to decrease. And that ammeter that remains will actually give us an indication of the total current. So this is just an example. We'll take a short break for now. When we come back, we'll look at another, practical exam type of a problem. See you after the break. Welcome back to our session. We're still looking at circuit problems whereby we are going to take internal resistance of the source or the battery into account and try and apply the guidelines as we would have discussed them in terms of approaching these circuit problems. Right. So here is an example which says in the circuit shown, we'll show the circuit shortly, the battery has an unknown EMF and an internal resistance. So what is not known in this scenario is the EMF, okay, which is not a trench smash. So our EMF, question mark, we don't know what it is. But also this battery has an internal resistance. So that small resistor inside the battery has a magnitude of 0.8 ohms, right? So that's the starting point, okay? Then there are 3 resistors in the external circuit. Okay, and what is important also to note is that the 6 ohm and the 4 ohm resistor are connected in parallel. But let's look at what the questions say. It says here, when switch S is closed, the reading on the ammeter A2 is 0.6 amperes. So the question demands that we calculate the reading on voltmeter V1. Right, so here is our circuit, right? A2 reads 0.6 amperes. So we want to calculate the reading on the voltmeter V1. Right. So this is a straightforward and routine calculation. We need to ask ourselves, what exactly are we given? And then what is it that we are looking for? Okay. So according to this circuit, the current that goes through A2 is given as 0.6. Now this voltmeter V1 in not so many ways, it's equals to V parallel. Okay, so it measures V parallel, which is actually voltage across the 4 ohm. Okay, which is also equals to voltage across the 6 ohm. Okay, that's what it is. So we want to calculate V1. So we are going to apply the Ohm's law to actually determine V1. So we're saying V1 is equals to current multiplied by resistance. Okay, so V1 is equals to, which current are we talking about? The current passing through A2, which is 0.6 amperes. The resistance of that resistor through which the 0.6 amperes passes is 4 ohms, right? So then our V1 is equals to, if we can quickly determine that by means of a calculator, we have 0.6 multiplied by 4. Okay, what does that give us? 12/5, which is 2.4 volts. Right, so this is 2.4 volts. So if that is 2,4 volts, it means also this is also 2,4 volts, right? Why? Because we of this fact that V parallel is equals to V1, and we know that in a parallel combination of resistors, voltage remains constant. So this is a routine calculation. What's so important about it? You identify the correct formula, copy it as it is, okay? Then after that, do the necessary substitutions, and then get the final answer with the correct SI unit, okay? Right. Then there is a follow-up question that when switch S is closed, we're still saying the reading 0,6 on ammeter A2. Now we want to calculate the current passing through the 6 ohm resistor. Right. Now, there is a fact that we have established, right, that V1 is equals to V across 6 ohms, which we obtained to be, just to confirm, 2,4 volts, right? So this is like 2,4 volts, right, across the 6 ohm resistor, which is equals to V1. So V1 is equals to V across 6 ohms, which is equals to 2,4 volts. So we're using this value that we obtained. Now we want to calculate the current that passes through the 6 ohms. So the current that passes through 6 ohms, we're also going to apply the Ohm's law. Okay, the current through the 6 ohms is equals to voltage across 6 ohms, okay, which is also the same as V1 divided by the resistance, okay? Now, what do we have there? Current passing through the 6 ohms is equals to 2,4 divided by 6, right? So the current passing through the 6 ohm is equals to, we can use by the means of a calculator, we can safely say 2,4 divided by 6. This gives us 0,4 amperes, right? So this is 0,4 amperes. It's also very important for us to realize that the current through the 6 ohm is actually less than the current through the 4 ohm, because the 6 ohm is of a comparatively greater resistance than the 4 ohm. However, this gives us some idea because the total current is split between the 6 ohm and the 4 ohm. In other words, we are saying that the total current through the battery in the circuit is equals to current through the 6 ohm plus the current through the 4 ohm, okay? So what's the thinking behind this very important statement? We are saying that as long as there is a branch in a circuit, when two resistors are actually connected in parallel, current is split between the two. So if you add that current, it will give you the main current through the battery in the circuit. Right, so we have managed to answer that question, but it follows also that the total current in this case is the 0,2 plus the 0,4. Okay, 0,6 plus 0,4. Right. Okay, now they want us to calculate the reading on voltmeter V2. Where is V2? V2 is actually the voltage across the 5.8 ohm resistor. Right. There are some very critical questions that we need to ask ourselves. Are we in a position to get the amount of current through the 5 ohm resistor, 5.8 ohm resistor? Yes, indeed, because that is in series with the battery. It means the total current passing through the battery equals the current passing through the 5 ohm resistor. Right. Now, we are saying that total current in the circuit is equals to 0,6, okay, plus 0,4, okay. This gives us 1,0 amperes, right? So that's the current through the 5.8 ohm resistor, okay? This is equals to 1,0 amperes. Now the question wants us to determine V2, right? So we are saying that if we have an idea of how much current passes through that, we can therefore say V2 is equals to the main current in the circuit, because the 5.8 is in series with the battery, multiplied by its own resistance, it will give us the magnitude of V2. So our V2 is equals to 1 multiplied by 5.8. Right, so V2 is equals to 5.8 volts. Right. Now there's something also that you need to pay attention to. So if V2 is 5.8, right? 5.8 volts, and then V1, we managed to get V1, I think V1 was 2.4, just we'll verify that, 2.4 volts. So we are in a position to get a sense of, the external voltage in the circuit, right? Because this leads us to the next question, which says calculate the EMF of the battery. So we are interested in calculating the EMF of the battery, right? Now, because we know that E is not given, so we are saying that E is equals to I, right? External resistance plus the internal resistance. That's how the equation is given to us. Then we can say that we can find the equivalent resistance in the circuit. So by finding R parallel, okay? So R parallel in this case is the resistance of 6 and the 4 ohms. That is the branch part of the circuit. So that is, we can use product over sum. 6 multiplied by 4 divided by the sum, which is 10, right? So our R parallel is equals to 6 times 4, that gives us 24, divided by 10, which is 2.4 ohms, right? That's 2.4 ohms. Then the effective resistance in the circuit is equals to 2.4, okay, plus the 5.8. Okay, so our total resistance in the circuit becomes, okay, so what do we have? We have got 2.4, okay, plus 5.8, okay. This gives us 8.2. That's our external resistance, 8.2 ohms, right? So we're looking for our EMF. We've got the total current, which is 1 ampere. That is 8.2, right? 8.2, right? Plus our internal resistance that is given, which is 0.8, right? So our EMF in this case is going to be, so if we add that, it will give us 9 multiplied by 1, which is 9 volts, right? So that's how we managed to get to that, right? So we asked ourselves, first of all, how do we simplify the circuit? We appreciated that part of the circuit is actually in parallel, which is in series with that. Then as a result, we're able to apply the equations, and we also managed to obtain the equivalent resistance of the entire circuit, right? So these are just some of the examples that we decided to use for the purpose of our discussion in terms of applying the guidelines of solving different circuit problems. So what is important from this point going forward is that you try and expose yourself to as many scenarios as you possibly can, okay? And by that you become confident in how to solve the circuits. From now, I think because of time constraints, that's all the time we had for today. See you next time.